Welcome back, everyone, to another Forge College Explainer. So if you've been following along with our Solidity from Zero track, you already have the basics of function modifiers down. You know how to declare them, and you know they can completely alter how a function behaves. But today we're taking the training wheels off. We are diving into access control and validation with modifiers to solve one of the absolute most terrifying scenarios in Web3, leaving your smart contract door completely unguarded. Seriously, in the smart contract world, an unguarded function that changes state is basically like leaving a bank vault wide open on a busy sidewalk. Anyone can just walk right up, call your function, and wreak total havoc. So in this explainer, we're going to learn exactly how to lock that door, check IDs, and enforce the house rules. To really get this concept into our bones, I want you to adopt a very specific mental model. Think of a modifier like a bouncer at a wildly exclusive club. Just picture a massive no-nonsense checkpoint guard standing right in front of your function's door. This guard is holding a clipboard with a specific rule on it. When someone tries to call your function, this guard evaluates that rule. If the caller breaks the rule, well, the guard unceremoniously bounces them. In Solidity terms, that means the transaction reverts, the door slams shut, and an error gets thrown right in their face. But what if the caller actually follows the rules? Then the guard politely steps aside, opens the door, and allows the function's code to execute. It's an elegant, brilliantly simple system. Okay, let's take a quick look at the blueprint we've sketched out for today. We'll start with smart contract checkpoint guards, then we'll dive into access control and input validation. After that, we're going to look at combining guards, testing your defenses, and finally, we'll wrap it all up with our next steps. All right, let's jump right into part one, smart contract checkpoint guards. So as I mentioned, an unguarded contract is a massive vulnerability. We use these modifiers to centralize our security checks instead of, copying and pasting the exact same code across 20 different functions. And just to jog your memory, this little line of ink right here is where the magic happens, the underscore followed by a semicolon. In our bouncer analogy, this is the exact moment the guard steps aside. The guard runs their checks, and if everything looks solid, they hit this underscore, and the execution flow jumps right into your function body. Once the function finishes its job, the flow jumps right back to the modifier. It really is control flow at its finest. Moving right along, let's meet our first type of bouncer in section 2, access control, or as I like to call them, the VIPs. Now, this specific guard literally has one job and one job only, checking the ID of the person calling the function. They don't actually care what the function does. They just care if you have the authority to run it in the first place, like a contract owner trying to withdraw funds, for example. And here's what that looks like drawn out. This is the classic onlyOwner modifier. We use a require statement to check if msg.sender, which is the caller's address, is exactly equal to the owner variable we stored back when the contract was originally deployed. If they match, awesome, we hit our underscore and proceed. But if a stranger tries to sneak in, the guard instantly slams the door and loudly shouts not owner through a megaphone, completely reverting the transaction. That string at the end is our revert reason, and it lets the caller know exactly why they got bounced. But, access control is really just half the battle. Let's look at section 3, input validation, essentially enforcing the rules. Because sometimes the VIP gets in, but they try to bring something, terrible inside. These guards enforce the dress code of the contract by checking the actual data you're passing in. A perfect example of this is guarding against the ghost visitor. See, in Ethereum, there's a very special address called the zero address, which is basically represented by a string of 40 zeros. If you accidentally send tokens or assign contract ownership to the zero address, those assets are effectively burned. They're lost forever in the void. So we create a nonZeroAddress modifier that strictly requires the address provided does not equal address of 0. Pass a zero address and the guard yells 0_address, ultimately saving you from a very, very expensive mistake. We can absolutely use these guards for numeric ranges too. Let's say you've got a function that mints tokens or processes a deposit. You might have a validAmount modifier that requires the input amount to be strictly greater than 0, because, a 0 deposit makes absolutely no sense, and maybe less than or equal to 1,000 just to prevent massive whale manipulation. If the input breaks these mathematical boundaries, boom, the guard immediately reverts the transaction with invalidAmount. It is a fantastic, proactive shield against bad data. Now, take a look at the weapon of choice our guards are using here. You might have seen both require and assert used in Solidity, but for modifiers, we strongly prefer require. And why is that? Well, it comes down to gas, the actual money used to pay for computing on the network.
When a require statement fails, it cleanly reverts the transaction, it undoes any state changes, and crucially, it refunds the caller's remaining unspent gas. It is a polite bounce. Assert, on the other hand, is really meant for checking internal logical invariants, things that should absolutely never happen unless there is a catastrophic bug deep in your code. If an assert fails, it panics and consumes every last drop of the remaining gas. So, for checking inputs and VIP lists, always stick to require. Give the user their gas money back.
So what happens when we stack them? That brings us to section 4, combining guards and why order matters. One of the most powerful things about modifiers is that you don't have to choose just one. You can completely stack them. You can have an access control bouncer standing right next to an input validation bouncer. But what actually happens when multiple guards stand in a row? Let's trace this timeline. If you attach onlyOwner first and validAmount second, Solidity executes them sequentially from left to right. The crucial point here is this. The very first guard to fail will slam the door, period. If a non-owner tries to call this function, step 1 evaluates to false. The transaction immediately reverts with not owner. The system doesn't even bother waking up the validAmount guard for step 2. It just short circuits. So a pro tip, always put your cheapest or most restrictive checks, like who is calling, first before running complex validations on what they're doing.
Okay, let's put this into practice. Section 5, testing your defenses.
Writing smart contracts without testing them is basically like installing a state-of-the-art security system and never actually checking if the alarms go off. No way. When we simulate this in a local environment, we essentially sketch out a testing ledger, just like this one. We define the call, who exactly is making it, what data they are bringing, and the expected result. Now, notice that 3 out of our 4 tests here are designed to fail. We actively want to see those reverts. If the owner calls it properly with a valid address, we expect success. But a non-owner, not owner. A zero address, zero address. A zero amount, invalid amount. By mapping all this out, we conclusively prove that our guards are reacting exactly the way we engineered them to. Which brings us to our final stop today, Section 6, checkpoint and next steps. So we have successfully gone from an unguarded, wide-open function to a perfectly layered, secure checkpoint. We've enforced ownership, we've validated parameters to prevent catastrophic data entry, and we've proven these defenses in a test environment. And I think this brilliantly illustrates our 3 core principles for today. First, centralize your logic with modifiers. Don't repeat yourself inside every single function. Second, always use require to give clear, explicit error messages and to save your users gas when they inevitably make a typo. And third, remember that stacking order absolutely matters. The sequence you list them in dictates exactly which bouncer checks the caller first. But before we wrap this up, I want to leave you with a bit of a provocative thought. Everything we've built and engineered today was for a single contract. But what happens when you start building massive Web3 applications with dozens of interacting contracts? Do you really want to copy and paste that exact same onlyOwner code into every single file? Probably not. So, how can we share these checkpoint guards elegantly across an entire ecosystem? Well, that is exactly what we will tackle in our next lesson on reusable modifiers and composition. Until then, thank you so much for joining me for this Forge College Explainer. I highly encourage you to go visit forge.college to dive deeper into the subject, grab all the code snippets, and continue your journey into mastering Web3. Keep practicing, keep those contracts guarded, and I will see you in the next one.